Hi everybody, welcome back. So here is the, we're going into, we've talked about the trigonometric functions, and we've talked about some of their properties, and in particular their periodicity, and now we're going to see what that translates into their graphs, and we'll be able to look at their graphs. Now, remember, the nice thing about trig functions is they're periodic. So that means we can expect their graphs to sort of repeat every so often. Okay, and that's exactly what happens. So we're first going to look at the sine function. And, when you're first working with a function, you want to see what the graph is. You might want to start out by plotting a few points. So these are the values of the sine function for the various angles. I just took these from the unit circle. And we can see that, in the first quadrant, when we go from 0 to pi over 2 radians, the sine goes from 0 to 1. And then in the second quadrant, when we go from pi over 2 to pi, it goes from 1 back to 0. And then in the third quadrant, it goes from 0 to negative 1. And then in the fourth quadrant, that is from 3 pi over 2 to 2 pi, it goes from negative 1 back to 0. And we can, if we plot these points, you can plot these points on these graphs, and then sort of get an idea of what the relative smoothness of the sine function. If we assume that, then if we just plot this from the graph from 0 to 2 pi, we get this picture, right? We go from 0 to 1, and then from 1 to 0, and 0 to a negative 1, and negative 1 to 0. Okay, so we get this part right here consists of one period or one cycle of the sine graph. And then, because we already know that the sine function has period 2 pi, then it just repeats. Okay, it repeats in this direction as well. Okay, so this is the graph of the sine function, and some things we hope are kind of obvious. Like we said, the period is 2 pi. It repeats every 2 pi radians. By the way, when we do this, we're always assuming that we're in radians. Now we're going to forget about degrees right now. The amplitude represents the height of the largest crest. That is how far we get from our center, and in this case, it's this distance, which is 1. We have several x-intercepts. In fact, we have infinitely many x-intercepts, and they're always going to be at multiples of pi. And the reason for that, of course, is by the unit circle. Okay, here's our unit circle. The only time when we have y coordinates are when we're at 0 degrees or 180 degrees, which is the same thing as 0, pi, or 2 pi, 3 pi, and so on. So those are the x-intercepts. Y-intercept, we can see we only have one of those, and that's at 0. It is symmetric to the origin because sine x is an odd function. And we can see that we have several peaks and several valleys. The peak, the fancy term for the peak is a relative maximum, and we have that occurs at when x is like pi over 2 or 5 pi over 2. We can see that the peak appears only once in a cycle. So it goes from pi over 2 to 5 pi over 2, that's 2 pi. So it's going to be occur when you have pi over 2 plus 2 pi k. That is k here. In this case, k, we're assuming k just to be integers like 0, plus or minus 1, and so on. And so that's where the relative minimum or the maximum happens, and the relative minimum occurs like at 3 pi over 2, negative pi over 2, or basically any negative pi over 2 plus any multiple of 2 pi k. Okay, and this is my mistake. I'm glad we caught this. The relative minimum, the y coordinate at this point, of course, is negative 1. So that's. Thank you for watching this video. Well, then you can catch that mistake. All right. Cosine, something similar happens. We can see the cosine. Here are the values of the cosine In the first quadrant, cosine goes from 1 to 0, and then in the second quadrant goes from 0 to negative 1, and then in the third quadrant goes from negative 1 to 0, and in the fourth quadrant goes from 0 to 1. And so a cycle goes like this. Okay, it starts at the top, goes down to the bottom, and then goes right back to the top. So this consists of one cycle. And then we also know that cosine is periodic of 2 pi as well, so we can just extend this. So the period is 2 pi again, the amplitude is 1 again. The x-intercepts are going to occur at odd multiples of pi over 2. So this is pi over 2, 3 times pi over 2, 5 pi over 2, a negative 1 times pi over 2. So we have, they're going to occur when the x value is plus or minus k pi over 2, where k is an odd integer. And of course, the y-intercept is at the point 0, 1. We have a relative maximum. We have our peaks occurring at multiples of 2 pi, right? So that's at the 2 pi k, where k is an integer. And the relative minimum occurs at negative pi, this next one occurs at 3 pi. So it's going to be some odd number times k. Some odd number times k. That's when the relative minimum happens. And of course that occurs at negative 1. And of course it's an even function, so it's symmetric with respect to the y-axis, okay, which all graphs of even functions are. Okay. Now you can see that these the graph here of cosine and the graph here of sine look almost identical. Okay, except that they're slightly out of phase. Okay, I don't know if you can try this. Well, we'll forget about that. But what's going on here is that so this is the cosine and this is the sine. And you can see that they're off. They're almost the same, but they're horizontal shifts of each other. And in fact, that's exactly what happens. It turns out that the sine of x plus pi over 2 is equal to the cosine of x, and the sine of x is the cosine of x minus pi over 2. These two statements basically say the same thing, because if you replace if you assume this to be true, if you replace x with x minus pi over 2, you get this one. And then if you assume this to be true and you replace x with x plus pi over 2 into here, you get this. So these are the same, say the same thing. And they're both true because of this. I'll give you a quick sketch, and no, we won't be responsible for proving this on the test, but I think it's good to see why this holds, just going back to the unit circle, because that's where that's how we define these functions. This is a special case where theta is in the first quadrant. So here's theta. Now here we have the ray coming out of the origin of length 1. We have another one here where this is 90 degrees. And so of course the cosine is the x-coordinate of this point. So it makes sense that this, let's say if we call this A, then this cosine is going to be A. And the sine is the y-coordinate of this point, so if we call this B, then the sine of theta is B. All right. All right. So we have a cosine. Now we have this triangle here. What we're going to show is that this triangle and this triangle are in fact the same, because what happens is we know that this angle plus 90 degrees plus so that theta plus 90 degrees plus whatever this angle is has to equal 180 degrees, or pi radians. So I'm just going to call this, I'll call this beta. Okay, and we can see that beta plus 90 degrees. We'll use we use degrees very briefly here, is equal to 180 degrees. And what do we know about the sum of the angles of a triangle? We know from basic geometry that they also have to add to 180. So we have alpha, we have beta here, we have 90 degrees here. Well, this had better be theta. Okay, and similarly we see that this is theta, this is 90 degrees, so this had better be beta. And so what we have here is we have these three angles are the same as these three angles. This side is equal to this side. So by basic, geometry, from geometry, we see that these are in fact the same angles. They're congruent, right? So that means that this side is opposite theta. So this side has to be B, and this side has this side has length A. And so what does that mean? Well, the x coordinate here is going to be negative B, right? We're going B units to the left. So the x coordinate is negative B, and the y coordinate is A, because that's this distance, this height. Okay, so at A we said, so this is A. And so we get that so A is equal to the cosine of theta, but it's also equal to the sine of theta plus pi over 2. Okay, which is exactly what we have up here. So that's how we prove that if theta is in the second quadrant, or in the first quadrant. If you do this again, you can do this similarly for the other quadrants. Okay, it's just basically you're just taking these triangles and just rotate them so that they're going to be sitting on this line here. But okay, you can do that or not do that. But that's why this is true, and that's why these are off by pi over 2 radians, or 90 degrees, if you will. Okay, the only other thing we should mention here, a couple things, is if going back to transformations, which you learned in Math 128. If you have a function and you multiply it by a constant, if that's a positive constant, it's either going to stretch it vertically or contract it vertically. And if k is bigger than 1, then it stretches it, and if k is between 0 and 1, then it contracts it. Similarly, if you take x, the x variable, and just multiply it by kx, that changes things horizontally. If k is between 0 and 1, then it stretches the graph horizontally. If k is bigger than 1, it actually contracts horizontally. Kind of the opposite of what you would think. But the thing here is that when you multiply the x coordinate by a number, you're stretching it or contracting it horizontally. When you're multiplying the whole function or the y coordinate by a constant, you're stretching things or contracting or vertically or contracting things vertically. Okay. Other things you should know, if you put a minus sign in front of the whole function, you're changing the sign of all the y coordinates, so that means you're reflecting the graph through the x-axis. And if you just change the sign of the x coordinate, you're reflecting the graph through the y-axis. Okay. So just with that in mind, what we're going to be doing is, let's see what happens here if we look at some variations on sine x and here. 3 times the sine x, that's going to have the effect of stretching things vertically. Okay, and we're going to see in the next video how to do this, but here we have 3 where we get a new amplitude. Okay, where the y coordinates go from between negative 3 and 3, and the period is still going to be the same. So we're still going to have pi and 2 pi here. Okay. Okay, but we're stretching. These points don't change because if we multiply 0 by the y coordinate is 0, and if we multiply 0 by 3, we still get 0. Okay, so that's how that works. So if we get a vertical stretch here, if we have y equals the sine of 2x, here in this case we shrink things. the sine of anything is between 1 and -1, so the sine of 2x is going to be between 1 and -1. But now we've kind of compressed this a little bit. We have something like that, and in fact, this is going to be, we compressed this by a factor of 2. So here's pi, and then this center will be pi over 2. Okay. So the period changes. Whoops, the period changes, and the amplitude remains the same. Okay, so that's the main thing. If you do something on the outside, it affects the y values. If you do something on the inside, it affects the x values. All right, so we're gonna get some more concrete rules of how to graph some of these other trigonometric variations of the sine and cosine curve. So we'll see you next time.